So this is the third video on the mole. What you should be able to do by the end of this video is carry out any calculations dealing with a single substance in terms of, let's say you get a certain number of grams of a substance. Well, what would be the volume of that substance if it was a gas in liters, or how many particles are present, or how many atoms are present. So let's say, for example, you're starting off with 64 grams of oxygen. Well, this map kind of tells you how to handle the calculation. So hopefully you know that's 2 moles. But let's imagine that our mass is 64 grams. Right? Well, what are you essentially doing? The reason why you know that's 2 moles is because you're essentially dividing that by 32. So whenever you want to go from grams into moles, you're basically going to take your given mass, which I'm just going to write GM here, and you're going to put that over your gram formula mass, which means you're essentially dividing by the gram formula mass. If you want to go in the opposite direction, so let's say you had, and for our example now we have 2 moles. We know that's 2 moles, right? If we wanted to figure out what the mass of 2 moles were, we'd do something different. We'd multiply by the gram formula mass. And you should be seeing a pattern here as we go around this wheel-like diagram. Okay, so what would the volume of those 2 moles? Now notice, now I'm talking about moles, right? Because the mole is the central unit. Once we know this, we can go everywhere else in the diagram. So the first step is almost always going to be to convert to moles in a lot of questions. It is the central unit in terms of quantification of matter. So, okay, I've got 2 moles of gas. You know probably by now that that is 44.8 liters. Well, why is that? Well, when you go away from moles in this diagram, you're basically going to multiply by 22.4. Now, when I do factor label, it's going to look like this. 22.4 liters is 1 mole, okay, of whatever it is. That's what you're going to multiply. But essentially, you're multiplying by 22.4. If you want to go in the opposite direction, like let's say I had started you at 44.8 liters, you wouldn't multiply by 22.4. You would essentially divide by 22.4. And that would give you the number of moles. So far, what are we seeing here? Whenever we want to go into moles, we're dividing by something. Whenever we're trying to get out of moles, we're going to multiply by something. So now we can do number of particles. Well, we know what is 2 moles of particles? 2 moles of particles is 12 times 10 to the 23rd. We'll use the following words. We'll use the term molecule. Sometimes we'll use formula units, particularly when things are not made of molecules. Right? So it'll be like the number of NaCl's or the number of NaNO3s in a piece of sodium chloride or sodium nitrate, respectively. If we want to know how many, now how do we do that? When we left, we multiply by 6 times 10 to the 23rd. Again, I'm rounding here. Well, how do we do the other way? Well, if we start with 12 times 10 to the 23rd, we know that's 2 moles. We're going to divide by that same number, 6 times 10 to the 23rd. Now, to go in this last step here, you basically need to look at the formula. So if this was the number of particles, and let's say the formula was CaCl2, and let's say you wanted to know the number of ions, not the number of atoms, right? Well, for every one of these CaCl2s, there's 1 calcium and 2 chlorides. So the answer for this would be 36 times 10 to the 23rd. Okay, and so what you're basically doing is you're multiplying by the number of atoms. You can go backwards, but if you did, you'd have to divide. And that's basically your mole map all set out. One little caveat here that's really important is this is only for, this part of the thing right here is only for the volume of a gas. All right. If you're given the volume of something else, let's say if you were given the volume of, let's say, a piece of gold, let's say, right? You would have to do this in a different way. If you were given the volume of a piece of gold, you would have to convert that. You'd have to use density as your bridge. So you'd have to take your volume and use your density, and because you could use density, since density relates mass and volume, you essentially cross multiply. If you take your volume times your density, that would give you your mass. And then once your mass, you're over all the way over here, whoosh, in that part of the diagram. So if you're given the volume of something that's not a gas, you're going to end up using density. So what I'm going to do is I'm going to very methodically do a single problem, and the single problem will involve carbon dioxide, and I have a 12.00 liter sample, which means I'm not going to get nice even numbers. I can approximate what my answer is going to be, and you should be able to do that. However, you're not going to get the exact answer. So the first step would be to convert this into moles, and then we can get the answer for all the other questions. So just starting off, we would know that if we're going to go from liters to moles, we're going to divide by the volume of 1 mole of a gas. So we're assuming all of this, by the way, is at STP. It should have been put in the question. That's my mistake. So we'd have 22.4 liters is 1 mole of CO2. And you put the CO2 here too so that the liters in this cancel out and we get our exact precise answer. So I didn't round this number, but when I divided by 22.4, that's what I got, 0.53571 moles of CO2. Given that this I do not believe is an exact number, I believe it is an estimation. So I would actually have to round it right here, and the correct answer would be 0.536 moles of CO2. However, I'm going to use the unrounded number in subsequent calculations and just keep rounding to 3 significant digits. So I'm going to answer the next 2 questions, the number of molecules followed by the mass of the sample. And we have these numbers from the previous videos, so for every 1 mole of CO2, that's 6.022 times 10 to the 23rd molecules. All right, and for the mass, we would go 1 mole of CO2 is 44.01 grams. And note, I'm making these longer than 3 significant digits, so when I round, this is in fact my least accurate measurement over here. I'm going to give you the answers for both these, and then we're going to move forward. Okay, so when I do the first one here, I multiply it by 6.022 times 10 to the 23rd. The moles of CO2 cancel out. I'm going to round this to the proper answer now. The correct answer would be rounded to 3 sig figs, so the correct answer would be 3.23 times 10 to the 23rd molecules. And for the next one, I'm going to take the exact same situation. 1 mole CO2, I want to get the mass. So I'm going to take 0.5, and we expect to get an answer a little less than half of 40, a little more than half of 44, right? Because we have a little more than half a mole of CO2, and in fact we do. We get an answer of 23.576 grams, and I'm going to round right here again, so that's 3 sig figs, and so my answer is going to be 23.6 grams of CO2. That would be the mass of the CO2. Now the last two, the density of the sample problem really has nothing to do with doing all this hocus pocus here. It's a trick question essentially. Basically, it doesn't change as long as it's at STP. It's 44.01 grams is what you have in 22.4 liters, and that density was on the other page. And when you divide through, you get 1.96 grams per liter, and that's your density. Now, the number of atoms is basically, it's 3 times this number right here, isn't it? Because this is the number of molecules, and every molecule has 3 atoms. So I can just take this number right here and write it down again, 3.23 times 10 to the 23rd molecules of CO2. And for every 1 molecule, there are 3 atoms. And so my molecules of CO2 cancels out, and I get my answer, whatever 3 times that number is. So I go 3 times 3.23, and I get 9.69. So it's 9.69 times 10 to the 23rd atoms. I could have used this number over here and checked it, in which case I actually will, and I'll go 3.226 times 3. In that case, I get 9.69 as well. So not using this rounded number didn't have an impact. It's possible that it could have, but I checked and it works out the same both ways. And so this is our number of atoms, and that's basically all the stuff on introductory mole things that I want to talk about right now. Except for one quick thing. Sometimes they'll ask about the number of moles of atoms, and that can sometimes confuse students. So if you have, let's say, 2 CO2 in there as just a statement, this means you have 2 moles of CO2. Okay, that also means you have 12 times 10 to the 23rd molecules of CO2. This is a kind of a Regents almost level question because it's really kind of easy. If you have 2 moles of CO2, And each of those, that means you have this many molecules. That means you have 36 times 10 to the 23rd atoms. And I hope you know where I got that from by now. If you divide this by 6 times 10 to the 23rd, that will tell you the number of moles of atoms, which is basically you have 10 to 23rds cancel, 36 by 6 is 6, you get 6 moles of atoms. We did this in Regents chemistry. I basically said there's one atom here, 2 atoms here, 2 times 1 plus 2 is 6. 2 times basically 1 plus 2, which is 2 times 3, equals 6. The number of moles of atoms basically is, if you know how many moles of something you have, you can figure out the number of moles of atoms, etc. Anyway, good luck with the problems. I will give you something on empiric and molecular formulas, which is the last section, by the end of the weekend.